Welcome to this episode of Bone Hunt, Discovering Dinosaurs Using AI. Today we're going to look at bones and how you can know that what you found is in fact a fossilized bone. Imagine you're wandering around in the desert and you find something that appears to be a bone. That doesn't necessarily mean that it is what you may think it is. The bones of any animal, whether they are from mammals, dinosaurs, or people, have some common similarities. They are comprised of calcium and phosphates, and there are certain patterns in the bones themselves. If you look at a cross-sectional diagram, you'll see that the bones tend to have compact outer parts that follow the shapes of what the bone should be part of. For example, the femur, the tibia, the fibula, the spinal processes, or the skull. They tend to flow in the shape of whatever is natural for that animal. It's the compact outer part making up the outer sheath that makes us say, oh, that's a bone. Spongy bone is typically found in the interior, and this spongy interior is what makes bones lighter weight, but still able to maintain strength. Looking at that cross-section, you will see some things called osteons. Osteons are the concentric shell structure of bones that typically surround something called a haversian canal. The haversian canal transports the blood either in arteries, veins, or other kinds of small structures. These concentric circles of osteons are one of the things we are looking for. Now, if you were to look at a bone from the side and cut the bone so that you could see the compact bone on the right side and the interior of the bone on the left, then inside you would see this long grain structure. The bone kind of has a preferential flow. It almost looks as if it was painted with a paintbrush, and that compact bone will look almost painted in a linear pattern. All these things can tell you that you're looking at bone. Now, there are lookalikes and things that will fool you. Petrified wood looks a lot like bone. It also has a long, grainy structure. The difference is that no matter how you turn that sample of petrified wood around, you will always find a linear pattern. It can go up and down, left or right, but it will always be linear. If you look at a chunk of plywood, a root, or a branch cut from a tree, you will see a similar linear pattern. When you find a long grain structure on a fossil and you don't know if it's petrified wood or bone, you can look at the end to determine whether or not there are any osteons in it. It may have those compact lamella that start out as curvy linear parallel things and start turning into osteon patterns. If it's very well preserved bone, these osteons can be very small or microscopic, something you might not be able to see without a microscope. But bone decomposing in the desert for a long time prior to being fossilized may have very large bony patterns, and these osteons may be large as well. They could be anywhere from 1/10 of a millimeter to a millimeter, or even larger. This macroscopic study of the tissues is called histology. There's also osteology, which is the study of the shape, size, and proportions of bone structures, determining if there are condyles, processes, fenestra, etc. When you look at a bone, say about the size of a basketball, and it has these long spiky bits sticking up in regular patterns that would be or could be spinal processes, which would indicate that what you found is a vertebra. Ribs can be obvious after you've seen them many times. Limbs can be another matter, though. It can be difficult to distinguish one limb from another. Imagine you found a large dinosaur limb, and you'd swear that it could be a femur. It's so big. But sauropods, the long-necked dinosaurs, could get incredibly large, so a femur could be massive, over 1 foot in diameter or more, compared to the humerus or tibia or the fibula, which would be smaller in diameter, and yet to you, it would look very big. Sometimes the shape will at least tell you that it is a limb, and you may not know which one it is yet, but that's where research comes in. Once you understand the structure and the shape, you'll be able to begin identifying not only what the bone is, but what it could have belonged to. One of the reasons we can hope to identify bones we just found is due to its geological context, or where the bones reside. Context is critical. So looking at this map of the western United States, you'll see these spindly red pixels that denote where the Morrison Formation is exposed. The Morrison Formation is a famous bone bed dating back to the late Jurassic period, which according to geologists was about 155 million to 145 million years ago. Only certain casts of characters are actors in the Jurassic period, and we tend to bump into certain species more often than others. If you find a very large bone, diameter or long, you can probably make an educated guess that it's a sauropod bone. If you find a bone that was hollow, but the core has been filled with some other mineral like calcite, it is indicative of a theropod. Theropods were typically meat-eating, two-legged dinosaurs. Going back to our vertebra with the pokey bits making up the spinal process, if you find a smaller vertebra with these little spindly bones that run parallel to the grain of the bone, that may be a neck vertebra or a cervical vertebra. So, through context, shape, and size, you can begin identifying a species. In one case, we found what we knew was a fossil. We knew it was a dinosaur, but we couldn't identify the bone. It looked familiar, but I couldn't put my head around it. It looked tooth-like, but we knew it couldn't be a tooth. It was too big to be a tooth. What we determined it was the back end of a claw. If I had seen the tip of the claw, that would have given it away. But the tip was buried inside the sandstone, so all I saw was the base. It wasn't until I was driving home that I realized that it was a claw. And when I looked on the internet to confirm my suspicion, sure enough, it came back as an Allosaurus claw. Allosaurus claws have little blood channel that goes down the side. When we analyzed our photos and videos, we saw the characteristic blood channel. Identifying that Allosaurus helped us determine by context the remaining bones at that site. We now could put a name on it, at least a genus, to that pile of bones. We knew that we had the legs, some arms, some claws, some shoulders, and maybe even part of a skull of an Allosaurus. Now, you can't just rely on shape. You will find a lot of bones in a wash somewhere, in a parking lot, that are shaped or look like a bone. That doesn't mean it's a dinosaur bone by any stretch. Look at it, and if you see a lot of crystals in it, probably not a bone. If you look at something shaped like a bone with an outer grain and a long structure, get interested. If you can see some part of the interior of the bone where it's been fractured and you can begin to see osteons, now you know it's bone, not just by the shape. To further confuse you, there are minerals that look like bone. Selenite, or calcium sulfate, can look and grow in stringy, fibrous-looking patterns that can fool you with long-grained structures. But if you look at the end, you won't see osteons. Calcite can form patterns that look like that as well. Calcite is a little bit harder than selenite. Selenite you can scratch with your fingernail. That's the other way that you'll know selenite from calcite. You can scratch it with your fingernail. You can scratch calcite with a penny. So if you find the calcite crystals and they're growing that way, you probably didn't find a bone. And those things can fool you. They look very similar. Identifying structures, forms, patterns, and shapes can begin to tell you what you're looking at. But once again, there is this one concept that is very important. Context. Context plays a part in where you're going to look in terms of a geologic map. A geologic map will tell you on the Earth's surface a time frame or period for your geographical location. The map will tell you whether you're in the Triassic, Jurassic, Cretaceous, or some other period. Now let's say according to your map, you're in a Jurassic bone bed and you find a white bone fragment on the surface. You shouldn't conclude that this is a dinosaur bone. It could be a bone from a cow, a horse, an elk, a deer, or something else that died on that spot. So was what you found a modern day bone or an ancient bone? You can kind of tell by the heft of it sometimes, or if it clinks when you tap it. You can often differentiate it by sounds, as it doesn't sound the same if you tap a cow bone. I can tell modern day bones just by their shape from a mile away. I got thrown off once though when we found a horse tooth, which looked like a white piece of curved plastic. It was as hard as my knife and very hard on the Mohs hardness scale. Since I couldn't figure it out, I went to my friends in a paleontology group. I was giving a presentation and asked if anybody knew what this is. And a guy spoke up who knows mammals. He's a PhD studying ancient mammal bones. He says, "That's a horse tooth." He says, "I can't tell you if it's ancient or modern, but it's a horse tooth." And I was like, "Oh, well, that's amazing because it's right here in the Morrison." And he says, "Well, it's probably a more modern animal that wandered through there and died." Sometimes modern animals can fool you. We found fossilized teeth embedded in sandstone that we thought were dinosaur teeth from the Cretaceous. But then we started finding other things nearby that were obviously shark teeth. Imagine, we're finding shark teeth at 6,000 feet in elevation in New Mexico, in the desert. So context plays a big role. We found crocodiles here, and the crocodile bones look a lot like dinosaurs from both the Jurassic and the Cretaceous, but they're not technically dinosaurs. If you find one, you still celebrate because it's a cool find. They are technically different, but they will still have those patterns that the histology will dictate. These are just some of the considerations you use to determine that what you're finding is bone. And then, if you are sure that it is bone, what kind of bone is it? You can go to a university and talk to somebody in the biology or preferably a paleontology department if they have one to get some guidance on what it is that you found. Tell them what those GPS coordinates are and tell them all about it. Maybe you can go out on a dig like we got to do. We had the honor of finding and then helping the museum dig up the only Jurassic crocodilian that anyone has discovered in New Mexico, called a oneAPI. Well, that's all for this episode of Bone Hunt, discovering dinosaurs using AI. You can find links to resources, tools, and downloads, as well as where you can go to learn more about everything in the series in the description. Remember to like and share this video and subscribe to the Intel Software YouTube channel. In the next episode, we'll dig into where you can begin looking for dinosaur bones. The adventure continues.
Let the adventure begin. Yep.